Welcome to CO450 Computer Architectures. This is week 10. First of all, we're going to just do a quick recap on truth tables. So the following table shows outputs for all input combinations. So we have the Boolean function truth table for an OR gate here, and we have two inputs, A and B, and we see the output that we will get if those two inputs are put through an OR gate. So this table is called a truth table since the table indicates the one true outputs from that combination. So 0 and 0, 0 or 0 is 0. 1 or 0 will be 1 as an output because at least one input needs to be 1 in order to get an output with an OR gate. So 0 and 1 is also 1, and 1 and 1, 1 or 1 is also 1 because both inputs are 1 there. So the only output that we get where we get a 0 through an OR gate is if both or all the inputs are 0. So a quick recap again on logical AND. So an AND gate can have two or more inputs, and the truth table for a two input AND gate with A and B inputs is what we're seeing here below. So AND is defined as follows. So A and B will equal 1 if and only if A equals 1 and B equals 1. So as you can see, all the outputs are 0 apart from where all the inputs are 1. So input A and input B are 1. Then with an AND gate, then and only then do you get a 1 output. So we can also see here, again, logical AND. So the electronic circuit symbols for 2 and 4 input ANDs are what we're seeing here below. So they look like they're sort of squares with a rounded side on one side. So we see a 2 input electronic circuit symbol and a 4 input AND gate electronic circuit symbol. So regardless of the number of inputs, the output of AND is 1 if all the inputs are 1. And you can also see in the algebraic expression we have the dot. So it's A at dot B is the way we would express the AND logic gate in algebraic form. And with the logical OR, so an OR gate can have 2 or more inputs, of course. The truth table for 2 inputs, A or B, is what we are looking at here below. So OR is defined as follows. So A or B will equal 1 if either A or B or both will equal 1. So we can see there, and you can see the algebraic expression for OR is a plus symbol. So it says F equals A or B. So it's not A plus B. It's A or B, and you can see the 2 inputs there, A and B, and we see when we put them through an OR gate, we get the following outputs, which is basically all 1s apart from where all the inputs are 0. So mathematically, we represent A or B as A with a plus symbol and B. And the electronic circuit symbols for 2 and 4 input OR gates are what we're seeing here. So you can see that it's a bit like a triangular shape. It's got 3 sides to it, but they're all curves. So you've got a curve rounded back and then 2 curves coming together at a point, so like a triangle on its side pointing towards the right hand side there. So that's the electronic symbol that we would use when we're drawing out electronic circuits. So we use that as a representation for an OR gate, and the inputs are coming in from the left hand side. So a recap on the NOT gate. So NOT is the simplest logical function that we have. So 1 input and 1 output only, and NOT is defined as follows. So the output of F of NOT given input A is the complement or inverse of the input. So f equals not a, and you'll notice in the algebraic expression here where we have f equals not a, I know it's not a because there's a little line above the a, so the line above the a negates it, so it's basically saying not a because the line is just above that a letter there representing the output, so or sorry, representing the input, so not a. So if the input of not is 1, then the output is going to be 0. So if the input of not is 0, the output is 1. So essentially it reverses it. So the not function is also called an inversion, and the digital circuit which inverts is an inverter. So in, I think, multimedia logic, which is a little program we use for creating our diagrams, electronic circuit diagrams, then they call it an inverter because that's essentially what it's doing. It's inverting the signal. So whatever's coming in is then inverted to the opposite. So 0 coming in, inverted to 1 going out, and vice versa. So the electronic symbol for a not is a triangle, an actual triangle on its side, with a circle on the sort of nose of the triangle, the end of the triangle there on the right hand side. So it's triangle with a circle, and we have the input coming in from the left and going out of the right hand side of it. So again, another little recap on NAND and NOR gates. So not AND and not OR. So both NAND and NOR are composite functions. So the NAND function is an inverted AND gate, and a NOR is an inverted OR gate. So it's basically we're adding a NOT to an AND for NAND and a NOT to an OR gate for a NOR. And mathematically, we use a horizontal bar to indicate that inversion. So we can see that a NAND for A NAND B would be written as the same algebraic for A and B with the dot. So we have A and B with the dot, but then we have a line that goes across the entire length of that part of the algebraic expression. So it's basically saying this is not A and B. So that's NAND. And with the NOR, so it's A NOR B, and that would be written again as A or B, as we would still normally have an OR gate. So A plus symbol B, but we then have a line that negates the whole thing, and that goes across the whole thing. So it's not A or B. So the whole A or B is a not. And in terms of how we would put that into the electronic diagrams, we would show it as these are shown at the bottom here. So we have an AND, which shows the AND gate symbol, so the square with the rounded side on the right. Then the output of that goes straight into a NOT with the triangle with the circle on it. And again, I've got the algebraic expression there saying A and B, not A and B, as a NAND gate. The other way to do it, there's two ways to kind of represent this actually. So you can do it with the AND gate and then the NOT gate straight after us. So the output of the AND gate goes straight into the NOT gate and then outputs from there. And that's fine, but you can also sort of bring the two symbols together, and this is one way that they show it, just to save a bit of space in the diagram, I think, really. So you've got an AND gate, but it's got like a little circle, which is kind of the nose of the NOT on its output. So the little circle on just before as the output comes out, indicating NOT, and we do the same on the OR side as well. So we could represent it as an OR gate. In the electronic symbol, going into a NOT gate, so for NOR, or we could just use a little circle on the output of a normal OR gate symbol to represent a NOR gate. So two ways to draw the same thing, really. So you can use either one is acceptable, and I think in multimedia logic they show both, although you can do a separate NOT gate and hook it up like that if you like, and sometimes I do it that way just to show. Sometimes I use the full NOT gate because it's just a little bit easier to show, but you can combine it into that single symbol that represents NAND and NOR. So again, with these symbols, make sure you're familiar with the symbols for AND gates or OR gates, NAND and NOR gates, so that you're aware, and the NOT gate, of course, so that you're aware of those, and the algebraic expression with the bars across the top in order to represent NOTs, and the dot for and the plus sign for or. So a NAND then is a reverse of an and the NAND output is 1 unless all inputs are 1. And likewise, a NOR outputs 0 unless all inputs are 0. So if we look at the truth table for a NAND gate with, again, 2 inputs, A and B, we see that the output F is going to be 1 if both inputs are 0, or if we have 1 or 0 or 0, 1. And the only output that won't be when we have all the inputs being 1, which is the reverse of what we had with an AND gate. So it kind of inverses the AND gate truth table. And again with the OR gate, we were getting 1s for any combination where we had at least one input, apart from 0, 0, which was giving us a 0. Now in a NOR gate, again, we get the opposite. So it inverts it. So the only output where we get 1 now is where we have 0 inputs, essentially. Gives us a 1. So it's just important that we can do this. So this gives us some flexibility, really, in terms of how we can use this logical process and the truth tables we produce for it. So OR, AND, and NOT are what we call the fundamental logic gates. So they are, everything else is derived from them. So you only need to know those 3, really, and then any combination should give you all the logical outputs you'd ever need. And everything else is built from those. They're fundamental. So in terms of creating Boolean functions then, so digital circuits solve problems by performing Boolean transformations on binary numbers. So any computer function can be created by combinations of Boolean variables, and Boolean functions created in this way are called combinational logic, and they are time independent. So with combinational logic, we're putting logical operations together in order to transform binary numbers by the combinations of those Boolean functions and the gates that are in between. So we're putting electronic signals of 0 volt or 1 volt. Let's say, well, it's between 0 and 5 really, but it's either voltage or no voltage. We should probably look at it in that way. And we're putting those into logic gate circuits, and the output is then being transformed. So as you can see, the transformations are, well, if I just go back, so the truth tables at the bottom here for NAND gate and NOR gate, for example, we're transforming the input signals into a single output signal. So that's what I mean by transformation. So the transformation of those signals. So we had 2 OR gates, we had an OR gate coming together. We had an inputs which had no voltage on them. We get an output of 1, and then we could put that into another circuit as a new input, and that would transform it again into something based on the logic that's passing through. So in terms of electronic circuitry inside a computer or any computer function, it's about transforming the bits in order to get the result that you want on the other side, but you do that via these combination of logic functions. Now the other important thing is where I say they are time independent, that's because there's no timing mechanism on combinational logic circuits. So combinational logic circuits simply transform the inputs into outputs based on going through the logic gate. In other circuits, you will have a timing mechanism which can change the internal logic of those circuits based on the timing. So there can be a time circuit where the internal logic will shift based on where it is in a clock cycle, for example. So that introduces a whole new element of time variance into the logical process that you're working on. Now we're not going to touch on those for at all really. So we're going to look at combinational logic in this module mainly, which is a little bit easier to work on because you don't have to consider the time factor where you are in the cycle. So this is a bit more simple. So when a digital system is being designed, an engineer usually starts with a specification. So we call that a spec, which describes how the system performs when the system inputs are this and the output is that. Okay, so we have an idea of what inputs we're going to have, and we know what output we want to achieve. So that's the specification. So for any combination of inputs, we will want certain outputs, and that's what you're trying to arrive at when you're designing a system. So what do we want it to do? For example, if you were doing a circuit for digital maths, so we've got binary mathematics, which we looked at. So we looked at like AND. So when you look at adding together binary numbers, so we know that if you add 1 and 1, we do a process where we get 0 out and we have to carry a 1 somewhere else, don't we, in our addition process. So if you're designing the spec to do an addition process in a digital circuit, you would have to think about, okay, well, when the inputs are both 1, I'm going to want a 0 to come out, and I'm also going to want another 1 bit to be carried out somewhere else in the circuit. So that would be part of my design specification, basically. If it's 0 and 1, then I just want 1. If it's 0 and 0, I just want 0. So these are the sort of things that you think about if you're designing the circuitry for a computer system. What do you want it to do, and where do you want it to go? So once you've got your specification, we then need to go to a truth table from which we can derive our full Boolean expression, and then we can make our circuit. So you can't just jump in with the electronics and design electrical functions. You have to work through from what you want to achieve, which is the specification, to the truth table to get the internal logic that you're going to use to achieve that specification. And then once you've got the logic worked out and you've got your Boolean expression, then you can take it and make a circuit from it using electronic components. So that's kind of what we're doing here. So we're going to working our way through that process. So combinational logic then. So any Boolean function, which we call f as an output, maps a total of n, so we're using n as a variable, input. So it could be x1, x2, x3, x to the n in terms of inputs, into one output. Okay, so one output only. So a Boolean function f of n variables produces a single output for each unique combination of those inputs. So we need to remember there are only two Boolean variables, which are going to be 0 or 1, and a Boolean function in which the output of f depends only on the input variables is called combinational logic. So there's no timing factor in combinational logic, it's just purely what's going in through the logical change makes a transformation, makes the output. Okay, so in combinational logic we just purely have inputs coming in and an output's going out the other side. So no matter how complex a Boolean function can be, we will define it by using a truth table. So no matter how complicated it can get in terms of combinational logic, we can always work out and what the definition of that is by mapping it through with the truth table. So we do have some little recap exercises for this week from previous weeks. So we looked at some exercises from work that we would have covered in week 9. So we have that to do, and I'll just switch across to the exercise sheet for that. So here I am in my little exercise sheet at the beginning. So we've got recap on truth tables. So it's asking me to create a truth table for the following logic expression. So f equals not b and a and b, or not c or and d. So this is we can see we've got an and here, we've got not b, we've got an a and b, and we've got a not b and the output of a and b, or not C and D. So we need to work our way through this. The first thing you need to do when you've got a truth table like this is first work out all the combinations of inputs that you could potentially have. When we've got 4 inputs, so it's 2 to the 4, which means we're going to have 16 outputs. So and hopefully you remember from last week the quick way of creating all those outputs. So we don't sort of sit there and work our way through it. We have a quick method for doing this, working from left to right. Always start at 0. So in our first leftmost column, I'm just going to do the combination of 0 and then 1. So it's a pattern basically. So 0 and 1. So we just have the first there. Struggling with me. And then I'm just going to copy that pattern down. If you're doing it in Excel, it's actually a lot easier. Word is sometimes a bit fiddly for this. So please bear with me a second while I get it to do its thing. Let's just paste those in. Oops. Oh, okay. Copy that. And I just want to paste that pattern just into that first column of cells, basically. To make this. There we go. Right, now it's playing ball. There we go. Right, so 0, 1, 0, 1, 0, 1, all the way down 16 rows. And I know it's 16 because we've got 4 inputs. And if you've got 4 inputs, it's 2 to the 4. So that gives you the total combination. So any number of inputs, so if I had 2 inputs, it'd be 2 to the 2, which would be 4. So if I've got 3 inputs, 2 to the 3, so that'd be 8. And with 4 inputs, we've got 2 to the 4, so that's 16. So I've got 16 rows. So on the next input across, going towards the right hand side, then again we have a pattern of bits to put in. So again we start at 0, and this time we just have 2. So it goes 1, 2, just like the powers of 2. So now we're on 2 bits, so 2 zeros followed by 2 ones. And again, we can copy that and bring that down in this rather awkward way. There we go. That's all right. Working on paper is probably easier for this. And now we have 4. So 1, 2, 4, just like the pattern of base 2. So copy those. Like I say, if I was using Excel, I'd just drag it down, but Word, we have to kind of paste it in. Right, and finally, the last input here, well, we're going to have 8 ones, which is half the rows, and then followed by 8 zeros. And you should find that we get the combinations all the way from 0, 0, 0, all zeros, to all ones, and everything is in between is covered if you use that pattern. So start with, so it's 2's, base 2, so it's 1, 2, 4, 8, and if we had more, it'd go along, and obviously the number of rows is would be, with 2 inputs would be 4, and with 3 inputs it would be 8, and 4 inputs would be 16, and then if we had 5 inputs it would be 32, and so on, just like the powers of 2. So it's easy enough to work out the number of rows you need, and also then just do the patterns. 1, so 1 of 0, 1 of 1, copy down. 2, 2 of 0, 2 of 1, copy down. 4, 4 of 0, 4 of 1, copy down. 8, 8 of 0, 8 of 1, and so on. So the next one would be 16 zeros and 16 ones. And the pattern repeats for the number of rows that you need. So it's really easy to do a truth table in terms of the inputs. So now we need to work out, because in our little formula here, our expression, we've got not B. So we haven't got an input for not B, so we need one. So we need to work out what not B is. So not B is obviously the inverse of whatever B is. So B in our table here is 2 zeros followed by 2 ones, 2 zeros by 4 ones. So all I need to do is just reverse that. So it'll be, so when B is 0, it becomes 1 in a NOT gate. So because we've done a pattern, it's easy enough to invert that. So it's just the opposite basically. So again, just copy that. And we'll bring that pattern down. There we go. Right, okay. So that's not B. So where B is 0, we now have 1s. Where B is 1, we now have 0. Now we need to work out what A and B output would be. So what's the output of A and B? So as we know with an AND gate, we only get one out. If you look at the truth table for an AND gate, you only get one out where all the inputs, in this case both, are 1. So where we have 1 and 1 for A and B here, we'll get a 1 here. But at the moment, anything else will get 0. So 0 and 0 will obviously give us 0. 1 and 0 is 0. 0 and 1 is 1. There we go. 1 and 1, that's 1. Okay. 0 and 0, 0. So it's only the one where we have 2 1s, both A and B are 1, will we get that, which is there. So again, that's it. So that's the outputs of A and B. Now we can bring those together because we've got a column now for A and B, and we've got a column for not B. So this part of the expression was not B and A and B. So the output of A and B, because it's in brackets, with the input of not B. So let's do that. So we're just looking at these two columns. So 1 and 0 there. Again, for an AND gate, the only one that's going to give us a combination where we're going to have 1 is when they are both 1. So I'm looking for them both to be 1 in those 2 columns. Can I find it? Is there one? There isn't one, is there? At no time do those actually end up being 1 and 1. So there is no output. So not B and A and B is only ever going to produce zeros, which is an interesting combination, unless I've done something weird. And I'll just double check. Nope, that looks fine to me. So, okay, so we're good. So let's have a look at the next bit. So the next bit is C. Well, we've got to do not C and D, but let's work out C and D first. So what's C and D? So C and D here, we're looking at these 2 columns. And again, we're only going to get one where we have 2 1s in this case in those 2 columns, which is here. There we go. We have 2 1s there, and actually the next row as well for that one. So okay, so 1 there, and then going down all these 2, we have 1 here. So 2 zeros, and then 1 for that one. And then look, we've got a load here at the end. So we've got another those 3. So that's it. Okay. Good. Oh, I've been looking at the wrong columns. Hang on. This is where you've got to be a bit careful. And you see the mistake, I've looked at those 2. Not those 2. These 2, C and D. So I put a 0, I put 1 there when I shouldn't have done it. And I've done it above it as well. That's well caught. So don't make the same mistake. So some can be a little bit unwieldy when you're looking at these truth tables. Those 2 columns. So it's only these last inputs that are 1 and 1, I think, of the entire lot. So yeah, just those. So we caught that. So now we're going to do not C and D. So we need to invert this. So it's just the opposite. So where we've got 1 in C and D, sorry, we've got 0 in 1 in C and D, then it's not C and D. So that needs to be inverted. So just going to do output there. And that's it. And then these become 0. And finally, we're in a position to bring it all together. So we've now got not C and D. We've also got the first part of not B and A and B. So those 2 are brought together with the OR gate. So with an OR gate, at least one of those outputs needs to be 1 to get a 1 on the other side. If they're both 0, we won't. And you can see actually, sorry, it's this one and this one, isn't it? So again, making sure we get the right columns, looking at the right place. So that one is, well, actually all these where C and or D are all going to be 1. So it's going to go all the way down there. Because at least one of the inputs needs to be 1, get an output. And then these last ones are all zeros. There we go. So that's our final truth table for F output. Now, I appreciate that also when you come to these little expressions like this, you think, well, what's the purpose of that? What's the point? Why am I doing this? Why is F? Why is it these combinations? Well, at this point, we're not interested, to be honest, in why. What I'm trying to give you practice on is being able to take an expression and turn it into a truth table, and that's really important, that you can do that conversion as I just did. So I just worked that way through. The actual expressions themselves don't really mean anything. They are just there to give you some combinational output, really. But obviously, if you're designing electronic circuits, then you would have an idea in mind. That's your specification, and you design that circuit to do it in something specific, and that's what we're going to move on to in this week. But these expressions that I'm giving you may not really do anything particularly. They're just there to test that you can actually unpick them, as you would need to, of course, if you were designing a circuit or designing a truth table from this. So it's not wasted. It's just that you don't need to worry too much about the why the outputs are like this. Just a question of working logically through the expression, really. So let's come down. So we've got another one here. So create a truth table for the following logic expression. So again, I've got 4 inputs, A, B, C, and D. So I need my combination. So just for quickness, I can copy that because it will be the same pattern of bits again. So I'm just going to take that and populate it. And again, if you're doing this in the TCA, then it's easy enough to quickly draw out a truth table, really. It's probably faster than doing it in Word like this. Okay, so what we got? So we got not A. Let's work out not A first, because we need to know that if we're going to combine it with an OR gate and not OR and so on. So let's do that first. So not A is the opposite to what we've got as A. So the pattern of A there is 0, 1. So let's go 1, 0. And again, we'll just copy that down because that's a quick way to get our approach. There we go. Right. And then we're looking at not A or B. So not A or B. Here's the B. So we're combining that column with not A here through an OR gate. So 0 or 1. So as long as we've got one of those input has a 1, then in an OR gate we're going to get 1 output. So that's 1 or 1. So this one's 0. 0 is not A and a 0 is B. So that will be 0. Here we have a 1 and 1. So yes. 0, 1, yes, so B is 1. Yep. Here we have a 0. 1 and 1, yep. 0 or 1, yes. 1 or 0, yes. 0, 0, that would be 0. 1 and 1. 0 or 1, that's fine. 0, 1, okay. 0, 0. Okay, and 1, 1, and 0, 1. Okay, so that's our logical output of not A or B, and then we do an inverse of that. So the line across the top there, across the whole thing, means that the whole output is being inverted. So it's a NOR gate really. So it's not A or B, but in a NOR gate as the output. So that's an inverse of this. So when this column is 1, this column will be 0. So let's invert. Whoops. That's just flipping the bits, essentially. That are in that not A or B column. So when that column's 0 like there, this becomes 1. When it's 1 like there, it becomes 0. That's it. That's flipped. Okay, so we've got the first part of our expression here. And then in the second part, we've got a not D. Let's work out what not D is. So not D is obviously the inverse of the D column. And again, we've got that pattern. So that was 8 bits that are 0 followed by 8 bits that are 1. So if we just invert it, we'll have 8 1 bits followed by 0 bits. There we go, so that's inverted that one. And then we're bringing them together, so C or not D. So here's the C column, and here's the not D column. Now we have to make sure we're looking across at the right columns, so 0 and 1. Remember with OR, we only need one input to be 1. So C is 0, D. Well, actually, where we've got the D's here, we know not D is always going to be where there's a 1. So as long as there's a 1 in that input, all these are going to be, doesn't really matter about C at this point. And then the rest of these are 0. So it should follow the same pattern as C over here. So we've got 4 zeros and then 4 1s. Okay, so 4 zeros and then 4 1s. That's it. Okay, good. That's our not C or D, or C or not D. And then finally, we're now in a position to bring together. So we've got C or not D worked out in this column, and we've got the not A or B in this one. So now we can, and it's brought together with an AND. So where we have an AND, they both have to be 1. All the inputs have to be 1 in order to get 1 as the outside. So if we got, so here we got 0 and 1. So again, that's going to give us 0. Here's a 1 and 1, so 1 in there, 1 in there, so 1. That's a 0. 0, 0. Oh, 1 and 1, yep. 0, 0. That's all zeros. Well, we have 0 this end, this end. Okay. 0. 1 and 1, that's it. Okay. And the last 2 are zeros. And there we go. That's it. That's the truth table developed with the final output as F. So we just did it a bit at a time. The thing with these, taking these formulas back to a truth table is just do it a little bit at a time. So we had to work out what not A was. We had to work out what not A or B was. Then we had to invert it because it's got the inverter across the top. So not A or B. Then we had to work out not D, and then we had to put it with the OR gate with C or not D, work that out, and then finally we could bring it together with the AND gate between those two columns. So it's just a step-by-step process, working our way through the expression, logically evaluating and creating a truth table for each part, and then bringing it together to give us our final output. Okay. So the next thing is we have a little recap on building logic circuits from these expressions. So creating a logic circuit design for the following logic expression. So we have here F equals A or B and C. So what I need to do is create this in multimedia logic. Now I'll do it in multimedia logic because I can't draw on the screen really, and draw it obviously in paper and pencil. It's a lot easier to draw out the logic circuit design, and a matter of seconds. So what I'm going to do is take this expression and I'm going to build that in multimedia logic, hopefully. So I'll switch over to multimedia logic. So here I am in multimedia logic now, and I want to create my F equals A or B and C. So let's have some inputs first. So here's my little switches I'm going to use as my inputs, and let's zoom in a bit. Let's get a bit small. So I need 3 inputs, A, B, and C. So I'm just going to put these on the left-hand side there, and we need some little labels just to show us what they are. So that's A, and just going to need 3 labels. So B, C there. The way I created those, by the way, if you're thinking, how did he just do a copy of those? Just like in any other like Word program and sort of Microsoft stuff, you can just do Control Drag, and that'll make a copy in multimedia logic. and you can drag a magic box to select a few and delete them with the delete key. So nice and simple just to create one. I find it's easy to create one and then just relabel it on a copy. So there we have inputs A, B, C, and we need to look at this. So we've got an OR gate. So it's A or B. So we hook up A or B, and then we're taking the output of that into an AND gate with C. So here's an AND gate. So oops, sorry, double clicked. Click and drag. There we go. So the output of the OR into the AND gate C, and we'll just put a little LED at the end here, which we will label up as F. So there we go. Perfect. Right. So that's it. So that's F equals A or B and C. So the A or B and the output C brought together with the AND gate there in a logic circuit. So that's what I would draw in my on my sheet. So I'd use my OR symbol and my AND symbol and do my wires on the inputs coming in A, B, C. Okay, switch back to the exercise sheet. So the next example question here is F equals not A or B and not C or D. So we can do that as an expression as well. So again, let's switch back to multimedia logic. So here we are in multimedia logic. So I've got a NOR gate for A or B, and a NAND gate for C and D, and I'm bringing them together with an AND. So we have to do, let's do the NOR gate first. So we could do OR, and then we could take the output and we could put it into the invert, which is the NOT gate. So that's one way to do NOR. So A or B, and the output then is inverted with an NOT gate from there. The other way to do it is to create an OR gate like that. And if I just click on it with the arrow, I double click, I bring up a little properties panel. This actually allows me, also it's an AND gate. I'm going to need that one of those as well, so I'll leave that there for a second. So sorry, an OR gate, double click on an OR gate, and you get a little option here for invert output as an OR. And that, if I do that, will show it with the little circle symbol at its end to indicate that it's a NOT on the output. So it's the same as this, OR into a NOT, but it's just combined into one logical diagram symbol. So that's a little bit easier on the diagramming. So it just makes it a little bit cleaner. So I'll just get rid of that, and we'll put the NOR gate in there. So we just wire that up with our inputs like so. And for here we needed an AND with a, again I could do it with an AND gate and a NOT, but rather than make it more complex, I can just do double click and tell it to be a NAND gate, which puts the NOT on the output there. So NOT C and D. And then they were coming all together with a normal AND gate. So an AND gate taking the outputs of both of those, like that, and then sending that off to F as output. Okay, so that's not C or D, and not, sorry, not A or B, and not C and D. Okay, so that's that expression built as a circuit. Let's go back to the exercise sheet. So finally, we have another little expression here. So we have F equals A, and then we got not C or D. and B. This one looks a little bit more complicated, but we can work through it in our circuit design. So we've got A being brought together, the output of not C or D, but through a NOR gate. So, and then being brought in with an AND. So it's okay. So it's not as complicated as it looks, I guess. But we have to work out this bit first. So let's do that. So notice C has a not above it. So this C is not C coming into the NOR gate. So with a little line across the C there, we have to do an invert of C before we bring it into the NOR gate. So it's a NOR gate, but it's the inverse of C, not C, that we're bringing in. So we need a not on C before we get into this NOR. So again, let's go back to multimedia logic. Okay, so here we are in multimedia logic, and let's sort out this rather complicated thing. So we've got not C. Let's do the invert on C. There we go, inverting C, and not C or D, nor D. So it's a NOR gate. Which we can do with our double click on the OR there, turn it into a NOR. So NOR C or D. And then the output of that, I'll just move it around so it looks a bit neater. Then we're going into our input into an AND here. Now notice we've got we're going to need 3 inputs on this AND gate actually, because we've got the output of here, got the outputs of these to go straight into this. Now there's only 2 shown, but if you double click, you can change that to 3 or 4. So we'll just up that to 3. And we'll just put this in. So there we go. And I think that's it. So A and not C nor D and B, I think. So that is the circuit that we want. So we can go back to the Excel sheet just to double check. Yep, there we go. So A or and not C nor D and B, and that was the circuit we created. Okay, so you can go from this. You can go from the functional expression to a circuit very quickly. I'll just go back to that circuit. So that's the circuit expression. Have that in your head, and then we'll jump back to the circuit that we built for it, and that's the circuit. So made from it. So you should be able to work your way back from an expression to a circuit and so on. And that's really what we're trying to achieve here. So you can do a logical creation of a circuit, a function, represent it as an expression, and then build it as an electronic circuit. We're not building electronic circuits, I know. We're just doing the design for it in multimedia logic as a circuit design. But we could then just get the components and put them together on a breadboard, and we would have that electronic components, and it would work as we're specifying it to work in the functional elements. So let's go back to the slides. So in combinational logic, any combinational logic function may be represented by 2 levels of logic. So one level of AND gates and another level of OR gates, which would be input inversion may also be required, but this is not considered a 3rd level. So if you go from AND gates to OR gates, that's one level to another level. Any NOT gates that you might do, or inverters, we don't count those as levels. So if you go from one input into a AND gate and then you go into an OR gate, that's one level to a 2nd level. So you're moving from AND gates to OR gates. So that's one way of looking at it. And we have these representations which we call sum of products, which we represent as SOP or SOP. And we also talk about product of sums, which is POS. So if I say SOP, I'm referring to sum of products. And if I say POS, then I'm referring to product of sums. And it's based on the either way you go from 1st level to 2nd level. So if we have AND functions into OR functions, or followed by OR functions, then we can say that we are doing sum of products representation. So that would be SOP. And a sum of products function in the expression would look something like this. So we have F equals A and B, or C and D. Now, if you look at that and you think about how that would be made as a circuit, we would see that the outputs of A and B are brought into an AND gate, and so are the outputs of C and D. And then both the outputs of those two parts in brackets, both the outputs of those OR gates, are then being brought into, sorry, both those outputs of the AND gates are being brought together by an OR gate. So the first level of the inputs, the first thing that the inputs go into is AND gates. And then the second level is the OR gate that they come together with. So the Boolean function F is the OR of the two functions A and B and C and D. So it is a SOP, sum of products, since the ANDs come first and then the OR gate. So first level AND and then the OR gates. If we were to invert any of the inputs, so here I've inputted all of them, I've inverted all of them, so we've got not A and not B, or not C and not D. That's also sum of products, because nots don't affect whether it's a sum of products or not. It's the AND into OR that makes it a sum of products, first of all. So it's relationship between AND and OR gates that affects whether it's a sum of products or products of sums, not the inverters or not gates. So we have a little handout exercise for sum of products representations, so SOP representations. I'll go to the handout now and have a look at that. So with these sum of products representations, we're just going to get you to create a logic circuit or circuit design from a SOP expression. So we have a SOP expression here, so F equals A and B, or C and D. Nice and easy, taken from what we were just looking at. So this is AND gates into an OR gate. So we're going to build that in multimedia logic. Okay, so we're back in multimedia logic, and we're going to create a SOP, sum of products. So AND gates first, two AND gates, and then an OR gate. So we take our inputs A and B into an AND gate, and C and D into AND gates, and then the output of those into the OR gate and onto F. Okay, so first level AND gates. They're the first things we come to. And then the second level, OR gate. ANDs into ORs. If you saw this circuit, you would say this is a sum of products circuit. And that's the other way to think about it. And we need, maybe in the TCA, I might give you a circuit like this and say, is this a sum of products circuit or product of sums? And you know now that sum of products means AND into OR. So you'd go, oh no, AND gates first, OR gate second. This must be a sum of products. That's what you need to know anyway. That's what you need to be thinking. Great, so let's go back to the exercise sheet. So that was that one, and we've got another one here. So what have we got here? So F equals, again, this is SOP logic, so we have not A and B, or C and not D. So we're just inverting the A and the D now. That will make no difference to it being a sum of products. It's still sum of products, even though we've got those inverts on A and D. So we can just do that in multimedia logic. So let's go over to there. So back in multimedia logic, and this is what we had previously. So now we're just going to invert A and D. So to keep that simple, I'm just going to unwire A and D here. And I'm just going to put a NOT gate, an inverter, between A and D so that they're coming into that AND gate like that. So probably just need to move some of these bits around a little bit. Oops. I'm going to move them across so I can kind of fit my NOT gate symbols in. And let's wire those in. There we go. So not A and B, or C and not D. There. So that's that circuit built. So that's the circuit that represents that expression. And then if we come down, so again, we've got to create a logic circuit design for following SOP, another SOP expression. So again, now we're doing NANDs. So we have a NAND here, and we still have not D, but we also have a NAND for C and D. So that also makes no difference. So the inverting to a NAND makes no difference. It's still essentially an AND gate going into an OR gate. So still sum of products. So let's go and alter our circuit to do this one. So back in multimedia logic, and the not AND was gone. So this is an inverted NAND gate now. I think we can turn that on without unwiring. Yes, we can. So that's that. And the inverter was still here. So the little line above the D, that's still the not. That has to remain. But we also had an AND gate on that, like that. There we go. That's it. So that's built. Okay, so if we come back, then here we've got our circuit, and that's built. Oh, we've got another one here. So final one for SOP, summer products. So now we have not A and B or C or and D. So the whole thing, the whole output of this entire circuit is being inverted. So you see there we got this whole output for the NOR. So we're going into a NOR gate basically, but that still doesn't affect it being summer products. It's still summer products because we've got AND into OR. First level AND, second level OR, even though we're negating it on the OR with and turning that into a NOR basically. So let's alter our circuit again to do that. So back in multimedia logic, and we've not got individual NANDs anymore. These are still ANDs, so we could convert them back to just straightforward ANDs. And we weren't doing the not on the D anymore. Now we're inverting here on NOR. So the NOR becomes, the output is inverted at the end. So that's our NOR. And that's that one. Okay, and we can compare that again to the expression. So that's the expression built as a circuit, and there is the actual expression for it. So F equals A, not A and B, or C and D. So it's the whole thing is inverted at the output of those. If these were still NANDs, by the way, you'd have a little line across the C and D part. And if you still had the knots on D and A, you'd have another little line just above those. So you might end up with like 3 lines sort of staggered above them. So it's the individual position of those lines that negates whether it's not C or not A or not A and B or NAND gate. So you might get 3 lines, you know, appearing, but you can see which they're not. So it's which the lines are. This line is going across the entire thing. So it has to be the OR. Because these are the inputs, these outputs of these 2 bits in brackets become the input to the OR. So this is negating the whole of that OR into a NOR gate, essentially. Let's go back to the presentation. So looking now at product of sums then, so if we have ORs followed by ANDs, then we say that we have a product of sums. So product of sums is like the opposite to sum of products. So this is a type of representation where we go from OR into AND. So first level OR gates, second level AND gates. So a product of sums POS would look like this. So F equals A or B and C or D. That's definitely a product of sums. So the first inputs, the first logical gate that the inputs go into are ORs, and then we go into an AND as our second level. So in this case, F is a Boolean of 2 OR functions, A or B or C or D, and it is product of sums POS because since the ORs come first and then the AND gate is at that sort of second level. And again, it doesn't matter if we've got negation on it, if we've got the inverts on it. So here at the bottom we've got F equals not A or B and not C or D. That doesn't make any difference to POS. And again, NORs and NANs wouldn't affect it in any way. So we're looking purely at whether it's OR into AND or AND into OR. So OR into AND is product of sums. And again, I've got some POS representations, product of sums representations that we can look at and create as a circuit to see how that looks when you're in the representational form. So I'll go back to the exercise sheet. So here we are in the exercise sheet. So the first one we've got to create is F equals A or B and C or D. So it's products of sums because we're OR gates first and then AND gate. And it's just a nice simple one to do. So we go to multimedia logic and build that. Okay, so in multimedia logic, and we can build that. So OR gates first, and we're bringing it into an AND gate. So OR's first, products of sums. So A or B, C or D, and then the outputs of either side of those, that's the bits in brackets, an expression being brought into our AND gate. That's a product of sums circuit. And back in the worksheet, then we've got another one to do here. So again, we're just negating or inverting A and D here. So F equals not A or B and C or not D. So we can just take the circuit and alter that. So multimedia logic, let's make an alteration to that. So just unwire A and D, and we'll put a NOT gate in there. So not A and not D. Move that down a little bit, create a bit more room. There we go. So not A or B and not C or not D. So they don't have any impact on whether it's still POS product sums because we're going from OR gate into AND gate. So that's that one. We've got a third one here. So create. So now we have F equals. So we've got the NORs, so not A or B, and not C or not D. So remember, there's a little line there. Not D has to remain inverted, but we're putting NOR gates, and we're taking the A is becoming A again into that NOR gate first. So again, let's just alter that. So in the diagram, we just need to, oops, get rid of the NOT here, and do that, and then we're just going to convert these OR gates into NOR gates by inverting the outputs. There we go, that's it. Simple change. Still products of sums, so even though these are NOR gates, we're still all going into AND. And then for the fourth one, the final one, we have F equals A or B and C or D, but the whole thing is negated. You see the NAND gate for all of that. So it's just a question of turning into a NAND gate. So let's go to our diagram again. So we just need to convert these back to regular ORs, take out the NOT, and convert this AND into a NAND gate. There we go, that's it. That's it. Right, okay, so that was just a quick demonstration really of the expressions in SOP and POS into circuits. So let's go back to the slides. So what about a truth table then to find the Boolean expressions that we want? So in a digital circuit design, inputs and outputs are defined, and since computer circuits use only binary numbers, input values will always be only 1 and 0, and the output will always be 1 and 0. So the engineer designs the stuff in the middle between input and output by, firstly, 1, defining the inputs and outputs that we want. Secondly, 2, make a truth table to represent the input-output relationship with combinational logic. 3, define a Boolean expression in either sum of products or products of sums forms that satisfies the truth table. And then 4, finally, we construct a logic circuit that represents the stuff in the middle that performs the Boolean function on the inputs to get the desired output. So here's an example. So we have sum of products form, SOP. So we assume we have a specification that gives the outputs of f, function f, for the 8 possible combinations of inputs A, B, and C. So we have 3 inputs, A, B, and C, and we have specified certain outputs of f that we want to be 1. And if we're using sum of products, we define the outputs as what we call min terms or minimum terms. And min terms look for 1 as the output. So SOP is specifically interested in 1 output. So you can see here we only have 2 outputs that are 1 in the F column, our function output. So these are the ones that we would use to create our logic circuit. So here in sum of products. So with sum of products, we're working with AND gates first into OR. So we bring them together OR. So in terms of the min terms, we're using OR logic. So we're using AND logic. So where they're ones, we want ones. So it's A is a 1, B is a 1, and C is not 1, but C is 0. So it's not C. So remember, SOP looks for ones. If it is not a 1, then it must be the invert of it. So in the case of C here, which is 0, then we would have to invert C in order to make it 1. So we put an invert across the top of it. So in our little min term, we write it out in brackets as A and B and not C, because this is 0 and we want it to be 1. So not C would invert that back to 1. And then we write that out. So A and B and not C is what we write. So that's the min term for that output in sum of products. And the reason it's sum of products is because we're using AND gates and we're looking for ones. This other one, the other one we had here was there's a 1, there's a 0, and there's 1. So this is A and not B, because we're looking for ones, and this is a 0. So not B and C, because that's a 1. So A and not B and C is what we write out there in brackets. Okay, so this is establishing our min terms in terms of the expression. These are parts of the expression on the combinations that we want ones to be. So we're looking for ones, we use sum of products. So the output is true, or 1, for only 2 combinations of the inputs. If we make the Boolean expression using sum of products, the first level, which has the most terms, will only have 2 AND terms. We then define the 2 AND functions that result in ones being output. So remember, we're looking for ones output in sum of products from the function f for each ABC combination. Now note that 2 AND functions are unique. So for ABC combination 0, 0, 1, f will only be 1 for f equals A, not B, and C. And for the ABC combination 1, 1, 0, f will only be 1 for f equals A and B and not C. Oh, actually, there's a little bit of a mistake on my slide here. I've just realised this is wrong. Let me just go back and correct that live. Apologies. Yeah, because the actual here it's 101, isn't it? It's not 11. That's 110, but this is 101, and I think I've written it the other way around. Yeah, here it should be 101. So that actually is a slight mistake, and I'm gonna correct it live on the video. Because that should be 101. So apologies for that, and I will correct it in the slides on the actual thing as well. I'm getting a live correction here in my video. Apologies for that. So it's 101, which is why it's A and not B and C. So that's correct. And the other one is A and B and not C. So yeah, that if that was confusing to you, that was just my mistake. But it was correct in here. So 101 there. So apologies. Okay. So those are the little min terms that we create for those two combinations. And so then in sum of products form, so now we complete the sum of products Boolean expression for the function, which will result in ones for the two cases. We know that sum of products form, the second level of Boolean operator will be an OR. So thus we define f as, so we take our min terms, which are the bits in brackets, as we've worked them out, and we bring them together in an OR. So the Boolean expression is now fully defined, and note that f equals 1 only for the two cases in the truth value. So if you run this circuit, if we built this circuit, we would only get 1 as an output as f for those two combinations of 101 and 110 in terms of the three inputs. Any other combination would give us 0. And you could try it out, build that circuit, multimedia logic, run it. You will see it operate. We'll probably do some of those in a second anyway. So in the handout, we've got some exercises for this specified sum of products expressions. So let's go to the handout. So here we are back in the handout now. So we've got to create a logic circuit design for the following specified logic expression that we have. So we have f equals not A and not B and C, or A and B and not C there. So let's do that one. So I'll go back to the multimedia logic. Okay, so here in multimedia logic, so we've got our inputs A, B, C. So the first part in brackets was with AND gate, so it's AND into OR. So there's our AND gate, and it's a free input. AND gate is what we need. And we have not on A and B. So in this example, so not A, not B. So they come in like that. And then we have C. Okay. So that's the first part in brackets of our first part of the expression. Move that back so it's a bit clearer, hopefully. And then the next bit in brackets, we had another AND gate. 3 inputs. That. And now what always confuses students is, and it may be confusing you, I don't know, maybe not, but it's how to wire this up, because you've used all your inputs, you think you've used your outputs here, but don't forget this is wiring, so we can just solder on more connectors to these circuits. So you don't go take any outputs from here, you just run it back from here. So with this one we got A and B and then not C. That. There we go. And then we just take those and they're going to go into an OR gate. So we have 2 outputs from the AND, so 2 sides to its expression. So there we go. Into the OR gate and off to F. So first level AND, second level OR. And we could test out this circuit if we ran the circuit. So to run it, just a play button up here, that moves it into simulation mode, and we should find that where we have these two as 0 and this is 1, we get a light, so that tells us a 1 output. So that's the not A, not B, C combination. And where we had not C and B and A, then we get 1. Any other combination will give us 0, which is not lit on the LED here. And you can run through all the combinations if you wanted to. 3 inputs gives you 8 different combinations, so you could run them through, and but you will find only these combinations, these 2 combinations, 0, 0, 1, and 110 give you an output of 1 in this circuit, as predicted in our truth table and built in our expression. Okay, let's go back to our exercise sheet. So back in the sheet, so specified product of sum expressions. So create a logic circuit with this one now. So we got so this is actually for product of sum. So this is the other way around. Let me actually go back to the presentation, I think, for this and show you that first. Okay, so back in the presentation, yeah, so Boolean notation, we have min terms and we have max terms. So sum of products is the more common form of notation. So in sum of products expression, we'd be going f equals, like we have here, so we've got f equals a and b and c, or a and c and d, or a and b and d, or b and c and d, which we could also write as f equals abc, or acd, or abd, or bcd. Notice we can remove the dots basically. So if two letters are next to each other, we assume that it's and. So in logical use of algebraic expression like this, we assume, like you would in other algebraic expression where you just simply do, you see it as a multiply. When you're using logic functions, then we assume that it's an and if two letters are together. So the and symbols are implied in this representation and are still used when the expression might not be clear if they are kind of left out. Since sum of products is more compact, it is called the minimum term form and the min term form, and the and components are min terms. Similarly, product of sums is often referred to as the max term form and the or's max terms, since the product of sums terms are essentially more unwieldy, so they look longer in the expression, and there's normally more of them. So that's the way round that we describe it as. So sum of products would be min terms, product of sums would be max terms. So here's an example for product of sums, a Boolean expression developed for that. So a product of sums representation will contain a first level of ORs, and in the sum of products example, we look for 1 outputs in F, but for POS, for products of sums, we look for outputs that are 0. So you build your circuit based on whether you're looking for 1s or you're looking for 0s. Now in this truth table, you can see that the F column contains far more 1s than it does 0s. So it's much more effective and efficient to build your circuit using product of sums in this case, because the 0 outputs there's only 2 of them. So that would make a much more elegant circuit. So we're looking for 0s. So in terms of the max terms, again, we create these for the individual F output. So we've got 2 here, and again, it's ORs, so it's ORs first and then AND. So ORs for the max terms. So, and we just look at what we got. So this is a 0, so A is a 0, so it's A, OR, and B is a 1. We're not looking for 1s when we're using product of sums, we're looking for 0s. So that must be inverted. So B is not B. So not B or C. So A or not B or C is the max term for that one. And then down here we've got 0, 1, 1. So again, we're looking for 0, so it must be A, or this must be not B or not C, because these are 1s and we want them to be inverted to 0. So A or not B or not C. And that's the max term for that one. Okay, so 2 max terms, and we'd bring them together with an AND. So again, products of sums, here F is 0 only for 2 combinations of A, B, C. We represent these conditions in max term form, and each max term will produce a 0 only for the exact OR expression. So we now complete the Boolean expression for the truth table, and since in product of sums the second level of logic will be an AND, we know that the 2 max terms must be ANDed together. Yep, so we take our 2 max terms that we had in our truth table and we just bring them together in an AND gate. So, and the full expression looks like that. So note, so F equals A or not B or C, and A or not B or not C. So the 2 max terms brought together in an AND gate. Note that F equals 0 only for the two cases in the truth table. So those two max terms is the only time, if we built this circuit, the only time we're going to get a 0 output, no light on our little LED in the multimedia logic, is going to be when we get 0, 1, 0 combination, or we get 0, 1, 1. Those are the only two outputs that we're going to get no light on our little LED for. So again, we've got a little exercise to build our little product of sums expression. So we're going to create a logic circuit design for the following product of sums expression. So f equals a or not b or c, and a or b or not c, which is basically the one we just were looking at. So let's go and create that in multimedia logic. Okay, so here in multimedia logic, so we're using ORs now. So ORs first level in a product of sums, going into AND second level. So we need more inputs on these. So let's do 3 inputs. Go for these. And we're going to need some NOT gates. So I think the first one was A or not B or C. I'm going to shift that around a little bit to make it a bit easier to define. And then on the other side we had A, and then we had not B and not C. So not B, not C. And we brought those into our AND logic circuit. And out to F. There we go. Okay, that's it. That's it built. So A, not B or C, and A or not B, not C, or not C, and that outputs as F. So only those combinations. So again, if I play my circuit, so the combinations that give us no light, remember it's 0 that we're looking at, so no light, would be that, so 0, 1, 0, and 0, 1, 1. And any other combination, we'll see we get 1 as an output, a light comes on effectively. So again, you could work your way through 8 combinations and you'd find that the logic is flawless. It matches that exactly as specified in our truth table. Let's go back to the slides. So sum products versus products of sums representations then. So any Boolean expression can be represented in either sum of products or product of sums form. If we represent f in sum of products form, we have f equals, so here from the table below, we have A and not B, or A and B. If we represent f in product sums, then we have f equals A or B, and A or not B. So you can see there from the 4 combinations that we have. So with this, then effectively, then we can do either or. So where we want zeros, we use our products of sums, and where we want 1 outputs, then we use our sum of products, and we can do that. Now in this case, it wouldn't matter which form we used, because we've got 2 outputs that are 1s and we've got 2 outputs that are 0s. So it wouldn't really matter which way you built it. You could either build it in SOP or you could build it in POS. There'd be no potential gain. You'd probably use sum of products only on the basis of sum of products is more common, min terms are more common, so we'd probably do it that way. But there would be no real advantage in this particular example of which way around you do it. I'm showing this so you can see that you would use 2 different approaches. And if you want to test that, by all means, build those two expressions in multimedia logic and try them out side by side. You'll see the combinations marry up. So either SOP or POS representation is correct. We pick the representation that is simplest to build. So the SOP form is used more frequently simply because the notation is easier that's relatively, but the POS form can have an advantage by making the Boolean function being represented much simpler to express. So they both have sort of slight advantages. Which one you use is really dependent on what outputs you're looking for. So if you have a truth table where there's only, out of say 8 combinations, you only have 2, or a minimal number, less than 4 outputs which are 1, then you would use SOP. If it was the other way around and you only had less than 4 that were 0, then you'd use POS. If they both have the same, so 4 outputs are 0, 4 outputs are 1, then it's up to you. But like I said, I'd probably go SOP because that's more common and it's more obviously used. So but it doesn't really matter. They both are correct. You can, even building a circuit using, if you had 6 outputs that were 0 and only 2 that were 1s, you could do it all in POS. It would be more expensive circuit. It wouldn't be very cost effective. It's not very efficient, but it'd still work. It's still correct potentially. But yeah, it's just so what we mean by correct is also what's efficient and effective and the best way to do it as well. So in this example, in this one below, we have note how the SOP form of the Boolean expression is essentially more simpler. So this is what I meant by having 6 of one and 2 of the other. So in this case, we've got 2 outputs out of 8, which are 1s. And when we're looking for the 1s outputs, then building it using sum of products is the ideal. So our expression with sum of products is very simple because we only have 2 min terms. If we did it in max terms, using products of sums, then we're going to have, like, in brackets, we're going to end up with 6 parts to our expression. That's going to be a lot more to wire up and build and complicated to work with. So we definitely want to use sum of products for this one. So again, we'll go back to our handout and we'll just have a look at the expressions and designing our circuit from the specification. Okay, so we're back into the exercise sheet. So now we're going sum of products expressions and circuit design from a specification. So what is the fully defined sum of products expression for the following specification? Truth table is what we're going to work out. So with sum of products, remember, we're looking for the 1 output. So we have 3 1 outputs here. So we've got these 2 and this one. So we've got 3 1 outputs. So these are going to be our min terms. So let's put our min terms in. So open brackets. And the combination here is 0, 0, 0. So these are not 1s to get our 1 output here. So this is going to be quite a few knots to do. So I've got my little equation tool on the go here. So I want not a. And remember, with this, we're going and into or. So we're going to need our and symbol. So let me just find that a second. So where are we? There, I think. There we go. So, oh, sorry. Always a bit interesting with the expression built in Word. So bear with me just a second. Whilst I... That's right, there we go. So that's it. And not B. And not B. And not C. Okay. Close brackets. There we go. So that's the first min term. And next one underneath. In fact, it may just be easier, just in Word here. Sorry, I'm gonna copy this, and just bring it down, and I can modify it for each one, just to save a bit of time, I think. Always a bit fiddly. Again, this is where paper and pencil really comes into its own sometimes. So now we have 1 0 0. So 1 0 0. So we're looking for 1. So A has to be a, not a not A. So A, and the other two are still not B and not C. So that's okay. And finally, we have all ones. So that's going to be C. That's going to be B. Oops. And that's going to be A. There we go. That's it. So there's the min terms for it. So finally, we need to actually define that. So let's put in our expression here. Oh, in fact, I can do it again. So let's just paste that in and modify it. So f equals, not A and not B or not C. And remember, these are brought into ORs. So, and then A, let's modify that slightly. And then OR, and this one should be A. Oh, yes, it's all of them. A, B, C. Oops. There we go. So again, this is easy when you do it on paper and pencil, but so f equals not A and not B and not C, or A and not B and not C, or A and B and C. So that would be the expression, and then we could build that in the multimedia logic, and we could draw out the diagram for it as a circuit diagram as well. So, well, let's go and do that then. Okay, so here we are in multimedia logic. Let's build our circuit. So, so we got our AND gates, and we need them to be a 3 input. And I'm going to need 3 of these, as I've got 3 min terms. Okay, let's do them one at a time. So the first one, they were all knots. So we're going to need 3 knots here as well. So there's my 3 knots. So the first one, it was not A. And it was not B. And it was not C. Okay. And in the second one, it was A, but it was not B and not C. And in the third one, it was simply A, B, and C. And then the OR gates, bringing them together. So the outputs, all those being brought together in the OR, second level. And the output going to F. That's it. Perfect. Okay, that's the circuit built. And we could test it again. We just run it. There we go, running. So we're looking for 1 output. There's the first one, so all zeros. 1 0 0. And finally, all ones. Any other combination is not going to give us our light. Okay, so that works fine. So back to the presentation. So back, yeah, so this is the next one to do in product of sums. So product of sums here, we need to define that expression now using max terms. So again, we've got our truth table and we've got the outputs that we want. Remember, this time we're looking for zeros with product of sums. So we only have 2 to create, so 2 max terms. So again, I'll insert my expression. In fact, I will just paste what I had before in just to get started. There we go. And then we can just alter it. The only difference here is we're using or, not ands. So remember with product sums, it's or into ands, that way around. So we're looking for zeros. This is A is a 1, so it's not A, but B and C are zeros, so they should just be B and C. That. And then on this one down here, and again, I'll just for speed, oops, just alter that. So again, we got A should be an A because it's a 0, or not B because it's a 1. I'm looking for 0, so C is also not C. So let's put a not in here. So not C. There we go. So those are the max terms for us. And again, we'll just fully form that as an expression. So let's just alter this. So F equals oops, not A or B or C, and then we need our goes into ands, and then open brackets, A or not B or not C. So not B, or whoops, not B or not C. There we go. Right, that's it. Oh, forgot my bracket at the end. Close the brackets. There we go. Okay, so we need to, the last thing we need to do is just create that circuit as a pos circuit. So F equals not A or B or C, and A or not B or not C. So let's go and build that in multimedia logic. So here in multimedia logic, and we've got our ORs. We have those. Oh, we only need 2 of those. Need 3 inputs on them. 2 max terms. And we're going to need some inverts. And oh, just to remind myself what the circuit was again, so let me just jump back to builder. So our circuit was not A or B or C, and then the other one was the other way around. So one is not A and the other one is not B and C. So okay, should be able to remember that. Oh, so we're back in the multimedia. I just realised you probably saw me jump back from the expression to here. I hadn't recorded, so I've just done that, talking to myself. I'll just rebuild it again. So sorry, I just realised I just hit. I thought I paused it and then hadn't done that. So rather than stop, let's just unwire this so you can see my wiring. So to your eyes, it just suddenly appeared. I'd actually sat here just building it and not realised I was recording you at that point. So let me just take out all the wires and save just re-editing the video completely. We can do that again. So right, okay, so the first one was not A, B or C, and then on the second one it was A, not B, not C, and they're going into an AND gate to be brought together. There we go. So you've seen that then. So that's what I just did. Sorry about that. I'm trying to edit my video as I'm creating it here. But there we go. So that expression now, if I run that, we can see the only time we get no light, 0, which is what we're looking for with product sums, don't forget. So 1, 0, 0, and then 0, 1, 1. Okay, so those two combinations of all the only two combinations that are going to give us no light or 0 on the output of F. Okay, so let's go back to the presentation. Into our presentation here. So finding the truth table from a sum of products expression, we can also go the other way, i.e. from the Boolean expression to the truth table. So if we consider the following sum of products expression, so notice it's ands in the brackets and we're going ors joined in together, so and into or, so this must be sum of products. So we've got F equals X and Y and Z, or X and Y and Z, or X and Y. Oh, I think something's, yes, something's gone a little bit wrong in my slide again. I should have some knots on these, I think, and I haven't got that. So we insert the one outputs in the truth table, and yeah, so this slide is slightly off. So, so I think I should have had, somebody should have been knots basically on that slide. So we're looking for the one output. In fact, we can do that now. Again, I'll just edit it live. Sorry about this. I don't know quite. I must be using slightly version slides or something. So let me just let's just change that, and then it's done. So let's make it just a random combination really. With this one, but we'll just put them in so that you can see what I meant. So what I should have had is things like this, just to give you an example of min terms that potentially have their combinations, and then we can talk about the combinations that you're seeing. I'll just negate a few of those letters. And again, I'll update my slides on that. Sorry about that. But good that I'm picking up on it now. I guess this addresses it. Yeah, so change that. Okay, so yeah, so what I was going to say with sum of products, because we're looking for ones with sum of products, so this would be 1, 0, 1. And I know that's a 0 because it's not Y. So because we're looking for ones, it's not a 1, so it must be a 0. So 1, 0, 1. And this one must be not X, so that must be 0, 1, 1. And this one must be 1, 1, 0. And this one must be 1, 1, 1. Okay, so I can identify the combinations within the truth table based on these three inputs, looking at this SOP Boolean expression by looking at where we got knots and where we've got not knots, as it were. So because we're looking for ones, where there's a not, this is not X, that must be 1, and where there's a not Y, in this case, then that must have been a 0. So 1, 0, 1. Yeah, hopefully you can see that. So you're looking for ones with sum of products is the thing to remember, and where you've got a not in your min term, that's going to mean that that's going to be a 0. So you can identify them in the expression. You can draw out the truth table for 3 inputs, X, Y, and Z, do all the combinations, and then you just look for those combinations of, in this case, like I say, 1, 0, 1, and you'd put that min term in there and as a 1 output. And the other one would be 0, 1, 1, and 1, 1, 0, and 1, 1, 1. Those 4 outputs must be 1s, and you could go that way as well. So again, I've got this as a little exercise. So we'll go to the exercise sheet. So here's my exercise sheet then. So what was specified truth table F that was used to develop the following sum of products expression? Okay, so let's have a look. So we've got A and B and C. So let's see now. So sum of products and into OR. So we're looking for 1s. So A, B, C must have been all the 1s. So it must be that one. Yep. And then the next min term, we've got not A, B, and not C. So we must have 0, 1, 0. So 0, 1, 0. Where is that? 0, 1, 0. Can't see the wood for the trees. Oh, there it is, 0, 1, 0, that one. And then finally, we have not A, not B, and C, so that must be 0, 0, 1. 0, 0, 1, 0, 0, 1. There, that's it. Those are the one out. They're the min terms. And the others, by default, must be zeros. Yep. Okay, so that was the truth table that was used to develop this expression. So you can go from the expression back to the truth table. And here's another one. So this is the other way around. So this is pos. So with pos, remember we're looking for zeros. So if it's like A here, that's going to be a 0. Where it's not B, that must have been a 1. Okay, so this must be 0, 1, 0. So 0, 1, 0. 0, 1, 0, that one. And remember the output will be zeros because we're looking for zeros with products of sums. So that's 0. And then we've got, what have we got? 0, 0, 1. C is not C, so it must have been a 1. So 0, 0, 1. That one. And the output was 0. And on this final one, they're all knotted. So we've got not A, not B, not C. So that must be 0, 0, 0. So that one is also 0. And again, what is not 0 must be 1. So the rest remain as 1. That's the truth table for that product of sums. Okay, oh, we got to the answers. That's the last of the exercise sheet. So back to the slides. So you want to be looking always for the simplest expression. So since Boolean expressions represent logical circuit functions that the engineer may want to build, it is always important to get the simplest Boolean circuit representation you can. So the simplest circuit is essentially the cheapest circuit to build. Unfortunately, even a SOP or a POS Boolean expression may not be in the simplest form. So we have some little theorems that we can use to help us to simplify our Boolean expressions. So we have some, these theorems are essentially rules really that we can apply to our maybe longer theorems, maybe our longer expressions, and actually simplify them somehow. So the first thing that we have is commutativity. Commutativity. I always struggle with that word. Commutative. They are commutative. Commutativity. But what this means is the Boolean functions and an OR are commutative, which means that if you said x and y equals y and x. So basically, it doesn't matter which way around you put it. So x and y is the same thing as saying y and x. And similarly, in POS, it'd be the same as saying x or y, which is the same as saying y or x. And that doesn't seem particularly groundbreaking at this point, but trust me, it'll pay off in a minute. So if we use the logic circuits, as you can see at the bottom there, we can basically build them, two ways round. It doesn't matter. So A and B coming in, or B and A. It doesn't matter which way round the inputs coming into the circuit. They're commutative in the sense of it works both ways. So it's a bit like 3 times 5 or 5 times 3. So in mathematics, you can put with multiplication, you can put the digits on either side, and you get the same result. And this is basically what we're doing with commutativity. I do stumble over that word. We're saying something that's commutative, but it means that we can actually, it doesn't matter which way round we put our inputs in. Distributivity, another word to stumble over, but the second rule is that A and OR functions are distributive, which means that if you see the example we have here, so we could have X and Y or Z, but we could also say X and Y or X and Z. So we can distribute X to the bracket part of our expression there. So we could put X and Y together, and we could put X and Z together with the OR, and we'd still get the same circuit. We can also say X or Y and Z, or we could say X or Y and X or Z. So again, we can distribute the X to the expression. So it just makes it a little bit shorter, simpler, to make it in that way. So we can illustrate our AND version of this relationship in the diagram below, and the OR version as well. So that just shows how we could make it a little bit simpler, really. So there you can see the two circuits side by side for the AND version. So our sum of products, for example, and you can see the two circuits side by side. We've lost a whole AND gate in the one on the left. So the left one is simpler. X and Y or Z actually makes a much more simpler circuit than saying X and Y or X and Z. So this is about trying to make things more compact and hence cheaper in the electronical world, because we're just making remember these translate into electronic circuits. So other fundamental sort of Boolean function theorems that can kind of help us, and this is just worth noting. Again, thinking about TCAs and so on, these theorems are just worth noting because they are what we use to try and simplify things. And again, it could just be a good question. Could be, give me a Boolean theorem, one of these here. So X or 0 is always going to be X. Yep. So it's 1 or 0. If X is a 1 or 0, it would always be still whatever X was. Yep. With an OR gate. So you can test these out. Just replace X with a 0 or 1, and you will see that these theorems hold. So on the OR side, so X or not X is always going to equal to 1. X or X is always going to be equal whatever X is, and X or 1 is always going to equal 1. In the AND side, we have X and 1, which will always be X. X and not X will always give you 0. X and X will always be whatever X is. And X or and 1, X and 0 will always give you 0. And we also note, and this is a bit of a head swimmer, most students go, what like that, just go what, but it is logically true, and it can be useful, and that's why it's mentioned here. So X equals not X. Okay, so if you invert X and then invert it again, you basically come back with X. So X can equal not X, which is a little bit of a swimmer in terms of your head, but that is logically true, and that may actually help us later on. So if we know that not X, if we end up with a situation where we have not X, we can just replace it with X, is basically what we're saying with these. So any of these things, so if we have a situation where we have X or not X, for example, well, that's just going to be one output. So I don't need that. If one's what I'm looking for, then I don't need it. So it's things like that. This is where these little theorems help us, because if that's fundamentally always true, we don't necessarily need to build it in the circuit if you're looking for a 1 or 0 or whatever x is. So, you know, it can help us kind of cut down on things if we automatically know the outcome, because these things are always true. We also have these things called De Morgan's laws. Now, De Morgan's laws gets a little bit complex, and to be honest, we're now pushing over into electronics and electronic circuitry design and things like that, which I think is a little bit, you know, I draw a line here really. So I'm gonna give you a little bit of De Morgan's laws, and it's useful to know what De Morgan's laws exist, and they're there for simplifying logic circuits in electronics. But that's all we really need to know. So this is just something to note really. So one of the other useful relationships in manipulating Boolean expressions is De Morgan's law. There are OR and AND versions of the law. So the OR version of De Morgan's law states that the complement of x or y is equal to x complement and y complement, or as it's expressed here, so we have not x or y is equal to not x and not y, and we also can state it as x or y equals not x and not y. And likewise, the AND version states that the complement of x and y is equal to x complement or y complement, or not x and y, which would equal not x or not y, which again we can state as x and y being equal to not x or not y. So again, these are things that are logically true. They sound expressions, and it's just a way of kind of, again, to be simplified. If these are always fundamentally true, then that's the law that states that. So we can use that in our circuit design. So if we want to simplify, so here we've got a SOP Boolean expression. So f equals a and b and c, or a and b and not c. We notice that we have the distributivity can come in, and we can express the above as actually being f equals a and b and c or not c. And we can also see in our theorem list that when we have C or not C, that always equals to 1. And in SOP, we're looking for 1. So we can then substitute F equals A and B and C or not C with A and B and 1, which eventually we can just say, because we're looking for 1s anyway, we can just simply say A and B. So f equals a and b is actually the much simpler and therefore the easier and cheaper circuit to build. Now, what may confuse you with this is you might think, well, hang on a minute, we had 3 inputs and they were A, B and C, and now you've got rid of C completely and just left with A and B. Yes, we have. It's just because B and you don't need to really put A and B through the AND gate and you're done. So we just assume that B, in terms of the result that we want, C is always on, and we don't really need C, so we ditched it effectively. So in terms of simplifying your circuit design, sometimes you end up with in this case, obviously we thought we needed maybe 3 inputs, and we actually only need 2 of them. So that's a good thing, because it means that we've now saved ourselves a bit of money and we've made something a bit cheaper, and we come down with something a lot easier. So don't forget, using these theorems, using these expressions, we're doing it on paper. This is mathematics on paper before we've actually made anything or built anything, okay? So we're working it through mathematically and logically before we buy components and start sticking them on a breadboard and building our electronics. So that's the whole purpose of this, really. So don't get too hung up if your simplification actually means that you lose inputs, or it's grossly simplified from what it was. Okay, well, thank you very much for that, going through the presentation. It's quite a tricky one this week, I think. It's quite a lot to think about. Do make sure you study this in depth. Sorry, there was a couple of little errors which I corrected obviously on the video, so you saw that I will correct the slides on Blackboard as well. Hopefully, if you looked at those in advance and were a bit puzzled, now it explained to you what that was on. Sorry about that. Things do sometimes go awry in PowerPoints, but we've corrected that. So anyway, hopefully go through that a few times, get used to the SOP and POS formats, and that should be good. Okay, thank you very much.